Hi, I'd like to talk with you today about optimization of functions. And specifically, I want to talk about critical points in relationship to the process of optimization. So I'll remind you what optimization is. That is finding minimum or maximum values of a function. Okay? We want to find either the minimum, maximum values of f, and probably their locations. Right? If we're like, where is the highest point in the state of Wisconsin? We want both. I want to know both like the coordinates of that point, as well as what is the actual elevation of that place, right? What was the highest temperature today? Oh, the highest temperature today was 72 degrees. Okay, what time did that happen at? I really want the location and the min and max. Okay, so there is a theorem, an absolutely true statement, a statement that's true beyond a shadow of a doubt, from now until the end of time. That maxima and minima, minima, the plural of minimum is minima. I don't know how that turned in. Minima, collectively called optima, or optimum in the singular. So optima occur at critical points, or at boundaries. Okay. So I wanted to talk about why that is. Okay. And I think that I want to do so first by drawing a picture, because I feel like the picture solves the problem, and I am a strongly picture-oriented person. And so anytime I can draw a picture to explain a phenomenon to myself, I am absolutely going to do that. Okay, so I've got a function, and we're talking about any function here. Ideally, it's differentiable in some places. If it's never differentiable, we have a real problem. Okay, so let's talk about a function, and let's say it lives in this interval right here. So I've got this function, and we're focusing our attention on the interval from A to B. So where are the optima between A and B? That's a good question. I think that we can just point them out. So I'll put a dot at the places where there are optima. There are optima here, 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 and then here, and then here. So I find these 5 places where I have a local min or a local max, relative min or relative max of my function. That is to say, a point that's lower than every other point nearby it. They occur at 2 types of places, really. So there's the stuff on the interior of the interval, like this point right here, where we have a horizontal tangent line. This point right here, where we have a horizontal tangent line, and this point right here, which has no tangent line defined to it. Okay, so these 3 points that I identified for you, those are what we call critical points. Okay, and so critical points are characterized that f prime of x is equal to 0 or undefined. So if either of those 2 things is true, then we call it a critical point. And the boundary points those are x equals a or x equals b. And so those are just the boundaries of the interval that you're considering. And so when you go to do an optimization problem, when you go to say find the minima and maxima, over some interval, you have to consider the critical points as well as the boundaries, okay? So I think that you should build a table when you do one of these problems. I feel like this table should contain f of x values and x values. It's going to be roughly broken into 2 blocks. I think that a block right here are going to be your crit points, and then I feel like you should have your boundary points in the second block as well. And then these are just, like the function values of the left-hand side. So evaluate the left-hand column to get the right-hand column, and then select the ones that are biggest. So I want to point out something subtle about this picture that I didn't make happen here. So let me draw a slightly different picture for you that highlights an important fact. Okay, so if we have this theorem, and we do, this theorem says that maxima and minima, optima, occur at critical points and boundaries. Is it guaranteed that you have an optimum at a critical point or on the boundary? And I want to draw a picture and show you an example of when these are not true. In particular, I want to show you that f prime equals 0 does not imply optimum. Okay, so the picture is as simple as this, like that. This could very easily be like f of x equals x cubed with my axes in different places. Okay, so looking at this picture right here, I've got this special point right here, and I've got a horizontal line there, right? F prime at, I don't want that to be a. Let's call that x tilde. Let's call this x tilde. F prime at x tilde equals 0, but you don't have an optimum there, right? Because if you go to the left, it's lower, and if you go to the right, it's bigger. We call these, well, it's a point where we have a change in concavity, or saddle point. What we want to emphasize to you is that if you want to find where the minima and maxima occur, then you need to build this table, and you have to have all your critical points with your boundaries. The critical points include f prime equals 0 and f prime does not exist / is like infinite or something like that. So build this table, but just because it's in the thing right here doesn't imply that you actually have a minima or maxima there. We've got to do something else in order to check whether we actually have a minimum or maximum there. And that's where the first and second derivative tests come in. And that's the subject for another video. Okay, so take the derivative, set it equal to 0. Take the derivative and find out where it doesn't exist. Find your boundary points, evaluate your functions. That's going to give you your table. But beware, the scary case when you have a saddle like this, and that's why you need the first and second derivative tests for extreme values. Thank you so much, and I wish you all the best today. Bye.